Thank you so much, Alexia, for the invitation and the introduction, and all the organizers for making this possible, and all of you who are up so late hanging out with us and listening today. So yes, I'm going to talk about abundance of triangles within fractal sets. I'm going to try to speed through some motivation and then try to give you some ideas of where this math is all coming from. So to set the stage, classic problem, the Erdős distinct distance problem that asks what's the least number of distinct distances determined by endpoints in the plane. Well, if you have endpoints, you can form and choose two distances which are on the order of magnitude n squared. And it's easy to have them all be different. And so Erdős's genius was realizing that the interesting question is, how low can you go? If you just look at a integer lattice, so you can think about these points as being integer values, so 0, 0, 1, 0, etc. You can start counting the distances. It's far easier to work with the distances squared, and in this integer lattice, you would have 1 squared, which is 1, root 2 squared, which is 2, etc. And the furthest you can go is diagonally across this lattice, which is root n squared by root n squared, and that adds up to 2n. So just immediate quick observations of this type tell you that the distances squared you're measuring are integers. They sit in between 1 and 2n. So surely there are no more than order of n of them. There are slightly fewer of them. There are about n over square root log n, because there are numbers like 3 that shouldn't appear in this list. And this is what Erdős conjectured roughly. And this is far lower than the n squared than if you just throw your points randomly down. And this is one of these big problems in extremal combinatorics or discrete geometry or wherever you want to classify it as, but was solved in the plane by Guth and Katz, who obtained n over log n. Yeah, okay, a little question there about the square root, but solved, right, power on n, but remains open in higher dimensions. And so this sets the stage. So a question from combinatorics and toward discrete geometry that motivates us to then ask, okay, what if I now want to leave this sort of discrete world to go to the continuous world, start looking at points where they're drawn from infinite sets and so forth. And so just to formalize this, then if I start with a subset of RD, then I'm going to write D of E to denote the distance set. And let's note that before, the question that Erdős asked was about number of distinct distances. He didn't care about repeats. And that is what set notation naturally does. So this is genuinely recording the number of distinct objects that you have. And so if you just rephrase what Guth and Katz did, then it gives a lower bound, asymptotic lower bound, on the order of n over log n on this distance set. It gives you about a growth. And I'm not dealing with constants, lower order terms, or anything of that sorts. But of course, we're pushing towards a continuous setting where I want to start taking a set that has infinitely many points. And then you can, of course, see that this goes to infinity. So if I have infinitely many points, I have infinitely many distances. So I need to rehash my question a little bit. So the idea here somehow should be that if the set that I start with is large, then surely I should have lots of distances. And now it's just a question of how I'm going to quantify that. And sort of I've ruled out that I'm going to quantify just counting the number of distances. So the most obvious thing that I could think of next after that is, well, trying to, measure, say with Lebesgue measure, or measuring the dimension of the distance set. Those could be very sort of clear ways to doing this. And so Steinhaus had this wonderful result, maybe originally stated on the real line, but it easily extends to higher dimensions, which is if you start with a subset of RD with positive Lebesgue measure, and you look at the different set, so I haven't even put distances on this yet, then this set contains a neighborhood of the origin. Of course, this immediately implies, if you then just look at the lengths that are involved, that if you start with a set of positive Lebesgue measure, then the distance set will have positive Lebesgue measure. And I threw here in parentheses and structured possibly, not only do we see that the Lebesgue measure of the distance set is positive, but in fact it contains an interval. So there's more structure sort of involved there. Now, you might want to say okay, there should be interesting questions here. What if I knew, say, that the Lebesgue measure of the set I started with was bigger than 5? Can I quantify precisely how large the Lebesgue measure of the distance set is? And I don't know how to do that very well. I learned recently from Malabika and Rani, her collaborator, that there exists some uniform bounds, like there exists some uniform constant here, that if you know it's above that, then you can say something uniform about the Lebesgue measure of the distance set, but it's like, it's a single number. It's not something that scales. And so there, even here at this level, I think there are still some interesting open questions here, but like also very interesting papers by Malabika, Pramanik, and Rani, her collaborator. Another thing, like, especially if there are grad students in the audience, like if you've done some measure theory and usually like, well, okay, you've done things on sets of positive measure, sets of zero measure, like who cares? So you might say, oh, it's done. But of course, in the title of this seminar series, One World Fractals, we care about sets of measure zero. So the question is, how can we push to them? Are there analogous questions? Can we break this condition of the Lebesgue measure of set needing to be positive? And so now we go into a fractal setting very naturally. And so this leads us to the Falconer distance problem, the famous Falconer distance problem, that then asks, sort of tries to reduce the conditions that we saw on the previous slide, and asks how large does the Hausdorff dimension of E need to be to guarantee that the Lebesgue measure is positive? So we're going to go into sets of measure zero. And so the question is, how low can we go and yet still be able to say that the Lebesgue measure of distance set is positive? Of course, one could ask also to weaken that and say, what's the Hausdorff dimension of the distance set? And there's some wonderful work there, Pablo among those, with Hong Wang and others that would contributed greatly. I'm going to focus on positive Lebesgue measure non-empty interior today, but there's like a whole storyline, could be a whole talk about just what happens if you measure the dimension of the distance set. Okay, so the Steinhaus theorem works in dimension one, works in all the integer dimensions. Already here, something different happens. In dimension one, you can construct a set that has Hausdorff dimension one, yet the Lebesgue measure of the distance set is zero with some digit restriction construction. So that's pretty bad news. So it just doesn't work in dimension one. But if you start looking at dimension two, then one can start playing around with constructions of sets. And based off of the lattice construction, now, of course, the lattice itself has measure zero. So one has to do this a little bit more smartly. So it's basically, you can imagine that you start with a lattice, then around each lattice point, you put a little disk. Now, of course, that is full measure at this point, but then you scale down into the unit cube. And you keep doing this, you add more and more points into your lattice, but then as the more points you put into the lattice, the more you shrink the disks around here. And by controlling how they shrink, you can create a set of whatever dimension you wish between 0 and d. And by just counting the number of distances really in the lattice, so just building on the Erdős distance problem somehow, or the counts that arise there, one can show that one can construct sets strictly less than d over 2 in dimension that have distance sets with Lebesgue measure 0. And so Falconer conjectured that, or this conjecture arose, contributed to Falconer, that d over 2 should be the threshold, that all sets with Hausdorff dimension above d over 2 should have distance sets with positive Lebesgue measure. And just to emphasize, because this sometimes throws people for a loop, if you have a set of lower Hausdorff dimension, then I'm not saying that it doesn't have a distance set with positive Lebesgue measure. Just take a line and it will have a nice distance set. So this is just in order to guarantee, so your enemies are sets that are incredibly sparse and like don't have connected components and things like that. And you're trying to guarantee that even though they're sparse and do all these bad things, that yet the distance set will have a positive Lebesgue measure. So that's our setting. Now, for some first results, when Falconer obtained the threshold of d over 2 plus a half, pretty impressive, like conjectured d over 2 and got most of the way there already in the first paper where he suggested the problem. And significantly later, so in the Steinhaus theorem, not only did you have positive Lebesgue measure of the distance set, but you also have non-empty interior, as in it contained a whole interval. Mattila-Sjölin matched that with the same threshold, d over 2 plus a half, significantly later. And this has been extended to a variety of different metrics by Josevich, Niels Morgul, and Crystal Taylor. And by now, even though some of these proofs were quite challenging back in the day, now it's been extremely streamlined. And so if you have a wonderful book like the book by Mattila that I'm holding up here, and then it's like 2 pages or so that just explain exactly how this goes. And because it's so pretty, it's so somewhat easy to present, I wanted to show you briefly how it works, because I think it will give you sort of context for some of the things that I do in extensions of these problems a little bit later on. So to give you an idea of how how one could view this now, sort of a modern viewpoint. So what are things that we need to know? First, we need to know, how do we encode the dimension of a set? And so the first thing for me is, if I start with a compact set with Hausdorff dimension that is given, then I can put a probability measure on it that somehow spreads the probability well enough, meaning that the measure of a ball is controlled by the radius to a power that is, well, almost a dimension. Okay? And so, of course, again, the Beck measure, like the volume of the ball, is the radius to the dimension, right? And so this is almost that kind of control. And this fits into Frostman's lemma, which, if you haven't seen, big thing, and can go both ways. Not only if you know something about the Hausdorff dimension do you get this, but the other way around. If you can build measures like this on a set, it tells you something about the dimension. There's also a notion of energy. If you have a measure of this type, then energies that are defined over here. So you have classic potential, like a Riesz potential. That's where the name perhaps comes from, energy. On the Fourier side, really it's about integrability of the square of the Fourier transform of the measure. Like that this is finite. And so to me as an analyst, like I started with a notion of Hausdorff dimension, and I'm like, how do I work with it? I know the definition, but like, how do I work with it? Like this has allowed me to A, put a measure on the set, and B, that I control some sort of a very concrete quantitative aspect of that measure. This makes it really wonderful for me to work with the Hausdorff dimension. And again, also here with energy integrals, if you know something about energy, it also tells you something about Hausdorff dimension. So I'm skipping all these connections. These are all beautifully explained, say, in Mattila's book and or other books, say, by Falconer. But these are the tools, just basic tools of geometric measure theory that we need to get started. So geometric measure theory preliminaries. What about distance sets? So for distance sets, what you can do is that you start with your set E, you know something about the Hausdorff dimension, you put a Frostman measure, so a probability measure where you control sort of the volume of a ball, you know the energy integral, you put that on the set. And what you then do is you create a push forward measure. So this delta mu is going to be a push forward measure. And to me, the way I read it is that it is it's a measure that measured the probability that the distance r arises. I already told you it was a probability measure. That was my first observation. It's very easy to see that if you just put in the indicator function of everything, and because the mu's are probability measures, then the push forward will be a probability measure. It's measuring the probability that a particular distance arises. And so understanding this measure surely should tell you then something about the distances. Like if most distances have probability 0, like surely there shouldn't be many distances, right? So understanding this one will be helpful. Now, what is challenging though to work with is that this measure mu, I mean, like it's supported perhaps on a fractal set. It's a tough object to work with. So as an analyst, it is very natural to replace it by an approximation and sub out for it like a smooth function mu sub epsilon. And you could think of mu sub epsilon as just being mu convolved with an approximate identity. And so as epsilon goes to 0, then in some sense you are converging back to mu, maybe in some weak sense. When you do that, when you write this push forward, then all of a sudden, because mu sub epsilon is a function, then it's really a function in front of dx. So these are far nicer to work with. And all of a sudden, what you can do is that you can say, oh, I'm going to do a change of variables. Like what I really want to isolate is this x minus y. And if I replace x minus y by, say, r omega, just switch to spherical coordinates, I can easily rewrite this in the following way, where I have isolated the distance between x and y. And then whatever is left is sitting here, and this sigma sub r is the natural measure on the sphere of radius r, and just comes from the fact that we switched to spherical coordinates, nothing more. And if we compare the two sites, what you can see is that this measure, this push forward measure that we created, we can see that it has a density, and the density is sitting right here in front of us. Now, of course, the trick is that, like, this mu epsilon, of course, it's a smooth version. I want to pass to a limit. I want to take a limit. So, like, do I actually think that I can pass to a limit here on the right-hand side and actually get something? Well, that we need to show. That is not obvious. Okay, so rehashing again. Just rewrote the density that we saw, and I'm abusing notation a little bit. I'm using the delta of mu epsilon both to designate the measure and its density, but I hope you so I apologize for that. Now, if we look at this, just a simple Plancherel allows us to throw a hat on each of the terms, and a mu of epsilon appears twice. You get a square of it, and you get an object that looks suspiciously similar to the energy integral that you had before. If only you had some help from this, from the Fourier decay on the natural measure on the sphere. Well, this is a classic sort of computation by stationary phase, computing the Fourier transform of the natural measure on the sphere. And sort of the punchline somehow is that it decays out at infinity, like d minus 1 over 2. And just so that nobody gets confused, like sometimes people want to plug in 0 here and tell me things explode. No, this is going to be bounded. This is bounded, and so this is a statement about decay at infinity. And if I sub this in to the density calculation over here, then it looks exactly like an energy integral. And if I make it look exactly like I wrote the energy integral as s minus d, and so I've just written this d minus 1 over 2 in a fancier way to like make it match exactly what happens in the energy integral, we get to conclude that if the set that we started with had dimension larger than d plus 1 over 2, then this density here must be bounded because the energy is bounded, and is bounded in the limit too. It's not only just bounded for mu itself, but also these mu epsilons. That's very easy to see. And then using a little bit more information, one can even see, like in terms of the r's, how these r's appear here is even going to be smooth, or I mean, continuous is all I need in the r's too. So this tells me a lot. So like I started with a push forward measure, and then it just took an approximation, calculated, saw that in the limit I have a density. This density is continuous. Lots of great things. Watch the punchline. The punchline is the push forward measure was a probability measure. Now this density that I have is bounded, so I can just rip it out by L infinity. What is left, the Lebesgue measure of the distance set, dividing by the L infinity norm of this density gives me a lower bound of the Lebesgue measure of the distance set, which is strictly bigger than 0. And I've shown that now a positive Lebesgue measure. So this is a proof of that first part. And then as soon as you know this, then the continuity of this density tells you that you will have non-empty interior, because it has to be positive somewhere. So it has to be positive in a little interval, and those distances must arise. That was it. That was a quick little proof of all these classic results. Now, writing the density yet again here, let me point out that the density that arises really could be rephrased, could be rewritten again as mu epsilon being paired with a convolution of mu epsilon with a sigma sub r. Really what is hiding here, this convolution of a function with a natural measure on the sphere, is really a spherical averaging operator. So the spherical averaging operator, what is it? It's an operator that takes in a function, and instead of evaluating at f of x, then what it takes, it replaces sort of f of x by the average of f on a sphere on a radius r around x. Okay, And so spherical averaging operators, they arise naturally. If you're doing kind of PDEs, they arise naturally as solutions to a wave equation and whatnot. Classic stories from like 1960s, 70s about like boundedness of these operators, LP improving, famous story from Stein about spherical maximal operators. They're all connected to this object. And somehow to me, it's really cool that it shows up sort of implicitly here. And one could phrase some of the statements that we had before as Sobolev bounds for the spherical averaging operator. And so they're underlying. Okay, these objects are quite well known and understood by now, but like even like within the last decade, there have been a number of interesting results on these things, such as how do maximal operators of these objects depend on the sets that you draw the radius from? Can you do sparse bounds? So these are still under active investigation, these sort of linear operators. Okay. Now you can see sort of from the calculations that I did before was that I ripped out the density by L infinity. You could go, Eyvi, what about just doing other, like, what about Hölder? Like, why don't you do some other smart things? And yes, one can. And so, for example, if you do by L2, all you would need to know is that the L2 norm of the density is bounded. And you can do the same thing, divide by it and see that you have positive look-back measure. And so modern improvements on this threshold, d plus 1 over 2, come from looking at the problem from this point of view. And so just to make a long story short, without going through any proofs or anything of the sorts, let me just say, here's what Falconer originally got, d over 2 plus a half, improved like 1990, 2005-ish by Wolf and Erdős, d over 2 plus a third. And then there's been a lot of progress in the last 5-ish years, like since 2018. I feel like I need to check on this slide every month. But to make a long story short, there are a number of papers behind here, a number of wonderful people. I hope I didn't forget anyone here. Eyvindur, Larry Guth, Alex Yosevich, Yuming Oh, Ken Ren, Hong Wang, Bobby Wilson, and Ruzhen Zhang. Basically, where it stands at the moment, or where they got was that they managed to improve a little bit over the d over 2 plus a third down to d over 2 plus a quarter plus a tiny little bit. This was improved to truly d over 2 plus a quarter in even dimensions. And then just last week on Monday on the archive popped a slight improvement, which went a little bit under a quarter if you're in dimensions 3 and higher. So like super active, lots of things happening, really cool, interesting harmonic analysis that's going on, decoupling and whatnot. But without commenting anymore on this, I wanted now to switch to like, okay, what am I going to look at? So distances are natural. Taking 2 points, you spit out just the distance between them. Just as you do that, you can look at all sorts of other configurations, put in whatever number of points you want, spit out whatever kind of configurations you have. For me, I like to look at triangles, natural sort of extension, taking 3 points, and then I'm going to spit out the 3 distances, a vector of the 3 distances that they form. And really, this is just saying, I view this as a triangle because if you tell me what the 3 side lengths are, I know which triangle you're talking about. It's just the side principle from sort of elementary geometry. And one can ask the same questions as Erdős did for distances. One can ask, what if you start with endpoints in the plane, how many distinct triangles do you have? Distinct triangles meaning in terms of congruence classes. Now, building on this resolution of the Erdős distance problem in the plane, Misha Rutniev wrote a short little note where he obtained n squared for triangles. Okay, note like how many triangles do you expect? You expect n choose 3, like if you just throw them randomly down, which grows like n cubed, and so n squared strictly lower. That's what Rutniev got. And this is achieved. Like if you just draw the regular n-gon, you get on the order of n squared. In higher dimensions, I don't really know what the answer should be. Okay, and it's open there. And one of the things that bugs me a lot is that I'm really bad at counting triangles. And you will see artifacts of that in some of the statements that I'm going to make in a second. So if we're going to go to the continuous version of this, what do? Well, we do the same thing as for distances. So here, d sub delta, or like d sub triangle v, that's going to be an analog of the distance set that you saw before. It's just going to spit out a vector of 3 distances generated by 3 points in my set. And now all I have to change is I'm going to say like, okay, how large does the Hausdorff dimension need to be so that the appropriate Lebesgue measure of this is positive, which here is the 3-dimensional Lebesgue measure. Because we're good at counting triangles in the plane, then there actually exists a nice threshold, 3/2 in the plane, which is different than the threshold for distances. Note, for distances, the threshold should be 1. But in higher dimensions, because I don't really know how to count triangles well, I only have the trivial threshold of d/2, as in dimensions 3 and higher, all I can say is if there are many triangles, there are many distances. And this is one of the embarrassments. I would love to have a better lower bound, but it connects to combinatorics. So I like to advertise this to combinatorics when I say them, like, can we count them better? Okay. What about positive results? Well, you can do all the same thing as for distances, as in you start with a set E, you know about the Hausdorff dimension, you know you can put a Frostman measure on it. From that, you can create a push forward measure that in your mind should be measuring the probability of a particular triangle arising. And you can ask, okay, does it have density? What can I say about the density? All these same things as we did for distances. Now, if you do this, you put in an approximation, you start changing variables so that this isolate is something that now looks a little bit more complicated than what you saw when you were dealing with distances. For example, let's just note the numerology. There's 1 mu of epsilon here. Before we had like a mu epsilon convolved with sigma r over here. Now this is more complicated. There are 2 of them over here. There's a more complicated measure. This measure arises from basically the set of triangles. You can think of it as like a natural measure on the set of a particular set of triangles. And so even the numerology is wrong. Like even if you wanted just to say, okay, put hats on each side, before we just had precisely 2 mu, so it like slammed straight into an energy integral. Here it's wrong. Like we have 3 of them. We can't just straight go to an energy integral. It makes it more complicated. And it's really because of this expression over here that things are harder. If I isolate that one, you could really think about that as an analog of the spherical averaging operator. You can think of this as a triangle averaging operator. That is, instead of replacing a function by an average on a sphere, it's like taking in 2 functions and replacing them, well, by an average over triangles in some sense. This is a multilinear integral operator. Like linear integral operator theory is somewhat well known, both singular and oscillatory ones. Multilinear, far less is known. And that sort of explains some of the complications. And me coming a little bit from harmonic analysis and multilinear integral operators, this is one of the things that drew me to this type of a problem. Further issues is that if you then think about this measure, how complicated is this measure? If you try to take the Fourier transform of it, well, it decays in far more challenging ways than the spherical one. The spherical one was in some sense easy, uniform decay in all directions. Here, it depends on which directions you go into, how much decay you get. Calculations over here really are due to Erdős and Bosch and Liu. It's actually not even trivial to calculate this Fourier transform. That's a rough calculation to do. They did it amazingly. I'm here sort of taking from a paper with a grad student, Mattila-Sjölin, and what we were doing over here sort of was emphasizing is that there's a portion here where you have uniform decay, like in the spherical one, but then there's another portion here that can disappear. Like this angle theta is the angle between the Fourier variables. So like if they're parallel, like whoosh, that disappears. You're just left with far less decay. In fact, in 2D, you have no decay. This complicates things tremendously. Now, just to give a quick sort of glance, there exist results on this. So the first ones, Erdős, Alan Greenleaf, they were really the first ones that introduced this problem, achieved a result in the plane. I was involved in with locus Fractals and extending it to higher dimensions. And then with Boach and Liu, we did the L2 method. There are some previous results that use very different techniques, projection type techniques that I'm not even going to touch upon, which are very cool. But you can see we have lots of thresholds. Remember, in higher dimensions, though, all we can do is d/2 as circles. So in 2D, where we actually have a good lower bound, like 3/2, well, we get 8/5. There's still a gap. We haven't solved it. Interesting. What about non-empty interior? Let me just say that Alan Greenleaf, Alex Josevich, and Crystal Taylor, they have a really cool technique figuring out sort of non-empty interior results for a variety of configurations. I just flashed one here quickly, but somehow the punchline was their technique couldn't handle triangles. So with a grad student, Francisco Romero Acosta, we were able to obtain sort of the first non-trivial Mattila-Sjölin type theorem, as in a theorem about non-empty interiorness of the triangle set. with a threshold 2/3 d plus 1. Okay, but basically everything that I've told you up to this point had to be changed somehow. We couldn't use the side. We need to use side, angle, side. We need to build on really cool work that Alex Josevich and Bochen Liu had done about the existence of triangles, which is a really cool problem too. Later, Alan Green, Alex Josevich, and Crystal Taylor were able to refine their techniques, which are really micro-local analysis type techniques. There was a double refinement. Yet, despite that, they were only able to match our results. And let me note that our results, like in dimension 3, this is trivial. It gives you 3. You're not going to find a set larger dimension 3. So like this is for dimensions 4 and higher. So the question asked remained, how low can you go? Can you go into dimension 3? And we were able, let me just skip this point and just say that we were able to achieve that. We got a concrete threshold, 23/8 in 3D, using the side, building on more recent work of Alex Josevich and Akos Magyar, and it extends beyond triangles into simplices, so tetrahedra in 3D, etc., or a result is in 4D. And so I think that's a good place to stop about the status of triangles. Thank you.
Thank you very much, Eyvi.
Sorry for going.